Some reactions readily form the products from the starting reactants, but others do not. This experiment studies how both the change in energy and order, or disorder, affects the progress of a reaction from reactants to products. The lab goals are to observe and then calculate enthalpy and entropy changes for solids dissolving in water, understand the rules of thumb for predicting entropy changes in a reaction, understand the sign conventions for delta G as they relate to spontaneity. Historically, it was thought that the heat change in a reaction was the only factor determining if a reaction was spontaneous or not. A modern single-use hand warmer is a typical example of a reaction giving off heat. Simply mix the contents of the plastic pack, and a salt solution helps facilitate the reaction of iron with oxygen to form Fe2O3, a spontaneous reaction that generates a considerable amount of heat. But there are cold packs, which absorb heat and feel very cold, that also spontaneously react, where either solid NH4NO3 or urea are mixed with water to form a solution. So clearly something in addition to heat change in a reaction, whether exothermic or endothermic, is affecting the spontaneity of a chemical reaction. It turns out that two factors determine if a reaction spontaneously converts reactants into products. The first involves the energy change, or enthalpy change, in a reaction. If a reaction is exothermic, in other words, gives off energy, then this energy change favors, but does not guarantee, a spontaneous reaction. If a reaction is endothermic, or absorbs energy, then this energy change inhibits a spontaneous reaction. The second factor involves the change in order during the reaction. That is, how does the order of the reactants compare to the order of the products? This factor is called entropy. Reactions that tend to become more disordered when converting reactants to products favor spontaneity. Those reactions whose products are more ordered than the reactants tend to be non-spontaneous. These two factors of enthalpy and entropy, along with the temperature of the reaction, determine if a reaction is or is not spontaneous. The factors of enthalpy, entropy, and temperature combine to form a fundamental equation relating all three to Gibbs free energy. The free energy change of the reaction is equal to the enthalpy change minus the product of the temperature times the entropy change. Those reactions whose delta G are negative are spontaneous, those with a positive delta G are non-spontaneous, or spontaneous in the reverse direction, and those with delta G equal to 0 are at equilibrium. In other words, no net change in concentration of products or reactants. If you've completed any experiments involving calorimetry, you have measured the temperature change of a reaction that is occurring in the calorimeter. This temperature change indicates whether a reaction is absorbing or giving off energy. A reaction that gives off energy in a calorimeter will show a temperature increase and is an exothermic reaction. A reaction showing a temperature decrease is one that absorbs energy and is an endothermic reaction. It can be useful to include the word heat in the balanced chemical equation. For an exothermic reaction, heat is written as a product in the balanced chemical equation. For an endothermic reaction, heat is written as a reactant. The inclusion of heat in a chemical equation can be useful when deciding how a temperature change affects a reaction at equilibrium. There are several rules of thumb which are useful when considering a change in entropy for a reaction. Entropy increases during a reaction if liquids or solutions form from solids, gases form from solids or liquids, there are more moles of products than reactants, or the temperature of the reaction increases. Graphs can be used to represent the change in enthalpy and entropy in a chemical reaction. For an endothermic reaction, products are higher in energy than reactants. For an exothermic reaction, the products are lower in energy than reactants. An increase in reaction entropy shows products higher in disorder. A decrease in reaction entropy has products lower in disorder.